In Lecture 9, we will cover Section 4.2. At the end of today's lecture, you should be able to apply node voltage analysis, abbreviated NVA, to circuits with independent current sources. To begin, let us review what we've done to analyze circuits. We've used KCL, KVL, and Ohm's law to solve for the behavior of our circuit, either a voltage potential existing across an element or the current running through an element. This has been cumbersome and non-systematic. Oftentimes we'd have to use a hodgepodge of KCL and KVL equations using Ohm's law to go in between. We want a formal, automated way to analyze our circuits. That is, we want to have a procedure or a list of steps that we can follow to determine the behavior of our circuit in a very systematic manner. Node voltage analysis strictly uses KCL and Ohm's law. That is to say, we will not use KVL in this analysis. Anytime we say we are using node voltage analysis, you must use Kirchhoff's current law. That is, we have to construct KCL equations at each of our nodes within our system. We will construct node voltages at these nodes of interest. And these node voltages will be based upon n number of nodes we have within our system. Therefore, NVA requires us to have n-1 KCL equations to solve for the behavior of our circuit. Recall the definition of a node, where a node connects two or more circuit elements. To begin, we have to introduce node convention. Looking at the circuit to the left, can you identify how many nodes we have? The answer is 2. That is, n would be equal to 2, and we denote our nodes by variables a and b. For NVA to work, we often have to identify a ground. A ground is a zero potential node, and what we'll do is select B as a ground for this example. Now our ground will be represented by the following symbol, where we assume we have a zero potential within our system. The node voltage at A and or B can be measured with respect to ground or another node. Lastly, recall we need n-1 KCL equations. By habit, we do not construct a KCL equation at our ground node. Rather, we construct our KCL equations at all other nodes within our system. Consider the following. We have a voltmeter on our left and a voltmeter on our right, where the positive terminals of both voltmeters are connected to the left and right hand side of our element respectively, and the negative terminals of our voltmeter are connected to ground. To determine our voltage drop across the element VA, we can construct a KVL loop around loop 1, such that minus V1 plus VA plus V2 is equal to 0, or the voltage potential across our element VA is equal to V1 less V2. That is, the node voltage at node 1 less the node voltage at node 2. That is to say, the potential across this element is the difference of potentials associated with their positive and negative terminals. Lastly, we can express a current running through a resistor. That is, if we have a resistor with resistance R and a voltage potential across the device such that we have V1 on the left-hand side and V2 on the right-hand side, we can subsequently determine the voltage drop across this element. Now, constructing an expression for the voltage potential across a resistor in terms of node voltage, we recognize the voltage drop across a resistor, V sub R, would be our potential at terminal 1, V1, less our potential at terminal 2, V2. That is, VR would be equal to V1 less V2. Now if we apply Ohm's law to this equation, our voltage potential across a resistor is equal to our current running through it times the resistance of a resistor. Equating these two expressions, we can say our current running through the element in terms of our node voltage is V1 less V2 per our resistance.